In our last two videos, we've taken a look at our models of friction, mostly static and kinetic friction, and talked a little bit about rolling friction. In this video, we're going to take a look at drag, and then also just do a few more examples of how to apply Newton's laws of motion. So we'll start with drag. This is another one of those that always opposes the motion. And I'll just go ahead and assume still air here. Otherwise, it's opposing the motion through the air, and you'd have to take into account the motion of the air, but I'm not going to do that here. I'm just going to say it that we're going to assume still air. So it'll always be anti-parallel to the velocity in that case. And remember, anti-parallel is just a fancy way of saying it always points in exactly the opposite direction of the velocity. Now, it turns out that there are multiple models of drag that get used. There are two regimes. One where the force of drag is linear to the velocity, but in most practical real-world situations, the force of drag is usually proportional to the square of the speed. So the usual way we write is 1/2 CD rho AV squared, where CD is the coefficient of drag. This will depend in part on the materials used, mostly how smooth they are or not. But that can be a little surprising. Certain rough surfaces can actually cause very smooth airflow due to some weird effects. This funny thing here is a lowercase Greek letter rho. It is not a letter P. And this is the density of the air. This is in kilograms per cubic meter. That's going to depend on the altitude you're at. To draw a rho, again, if we go back to the paper we all used in second grade, you start down here and you just go up like that and then resist with all your might the urge to turn it into a tadpole. All right. So it turns out that for a lot of things, like say if you're thinking about a skydiver or something like that, for a lot of typical surfaces, if you're not like super duper streamlining them, and yeah, this coefficient drag also depends on the shape of the object too as it goes through the air. For typical surfaces with the typical densities, this A here is the cross-sectional area. We'll get into that in just a second. You can roughly get away with saying it's approximately 1/4 of a kilogram per cubic meter times the cross-sectional area times V squared. All right. So let's go and take a look at an example of a skydiver and figure out how fast they'll end up falling through the air, what we call their terminal velocity. So we'll start first before the skydiver inflates their parachute. So let's say they're not a very good skydiver, so I don't have to redraw them. And they're just falling through the air feet first like this. The cross-sectional area would be the area that if you put like a light directly over them and you had a piece of paper directly underneath them, it would be the area of their shadow. So about that much right there. would be their cross-sectional area. Now, the part of the point of a parachute is when they inflate their parachute, like so, that just made their cross-sectional area a whole lot bigger. By making their cross-sectional area a whole lot bigger, they just made the force of drag a whole lot bigger on them. So let's start to see what kind of an effect that might have. So we'll go and take a look at a situation where you're at terminal velocity, which is another one of those weird names. Because in certain circumstances, you can be traveling faster than terminal velocity. So the idea is if you're going slower than terminal velocity, you'll work your way up to it. And if you're going faster than terminal velocity, you'll work your way down to it. But we'll take a look at that a bit more in a sec. So at first, when the skydiver is falling, their free body diagram might look something like this. Force of gravity down, drag up, and they're accelerating down as a result. But when they get to terminal velocity, what's going to happen is their force of gravity down and their force of drag up, are equal. And so then the acceleration is 0. So here, what's happening is as you fall down, you accelerate down, you pick up speed. As you pick up speed, the force of the drag gets bigger. Eventually, you'll get to a point where the force of drag is the same as the force of gravity, and the acceleration is 0, and the skydiver just falls at that velocity. Now, you can get to a case, and this happens, say, with like spacecraft re-entering from outer space and stuff like that. You can get to a case where in the upper atmosphere, where the density of the air is really low, the terminal velocities are quite high. And then as you get into the lower atmosphere, the densities increase. Because the density increases, the force of gravity doesn't change, but the drag will go up. And because you're going at this higher terminal velocity before, but now that the density's gone up, we'll see that the terminal velocity goes down. You can have the force of drag be bigger than gravity, and you accelerate upward, which means that you'll be going down, but slowing down. So if you're going slower than this point where the forces balance, you'll speed up until you do. If you're going faster than this point where the forces balance, you'll slow down until you do. So let's figure out this terminal velocity. Well, from Newton's second law of motion here, at this point here, when the acceleration is 0, we're going to just be saying that the drag is equal to the force of gravity. So we can just go ahead and plug in our models. 1/2 CD rho AV squared and mg. So let's go ahead and shuffle it all around. So if we solve for the velocity, let's see, v equals times by 2 mg over CD rho a, and take the square root. Cool. So we can take a look at this and start to see what might affect your what your terminal velocity is. How fast will you be falling through the sky? Well, if your coefficient of drag is small, that's in the denominator. That means you'll go faster. So if you wear like a slick parachute jumping outfit, that will make you fall down a little quicker. This rho is the density of the air. I was already talking about that. For that spaceship coming in from outer space, when you're in the upper atmosphere, this rho is really low. Terminal velocity is high. As you descend into the lower atmosphere, this rho starts getting bigger. And then suddenly the force of drag is now so big that it's bigger than the force of gravity, and you slow down to approach this new terminal velocity. Cross-sectional area is a big deal here too. So if the skydiver is going down at terminal velocity before they pulled their parachute, when they open up their chute, this area will be bigger. This area is in the denominator. That means that the terminal velocity will decrease. Again, same deal. The force of drag will have gotten a lot bigger, and the skydiver will accelerate upward so that while they're falling downward, so that they can slow down to land at a safer speed. Although, on a personal note, I do have a hard time understanding why people like to jump out of perfectly good airplanes. Although, if my airplane were malfunctioning horribly, I would probably be the first one out with a parachute. All right. So with that, let's go ahead and do just another application. Yeah, two applications of Newton's laws of motion here. So a classic problem, and we'll go ahead and we'll have some friction on this. So a nice consolidated problem. So I got my usual magic physics store pulley here. It's massless and all that. Same with all the strings involved. I'm going to go and stick a 2 kilogram block here. I'm going to say that the coefficient of kinetic friction here is 0.2. I'm going to tie it on a string, run that string over the pulley, and then let's say I have a M1 equals 1 kilogram block here. All right, so from our common sense of things, we know that at all times they have to be going at the same velocity, whatever that is, just in different directions. So the same speed. And they have to have the same magnitude of acceleration. Again, the direction of the acceleration will be different, but they have to be the same. The magnitudes have to be the same because if they weren't, the string would stretch, and we're assuming the string is done stretching. So with that, I'd like to find out what is the magnitude of each of my blocks' acceleration. Alrighty. So this is going to be a Newton's second law problem. I've got two objects moving, so I am free to analyze two systems here, and I will. So first we'll do force identification diagram here. This cuts through the string, so I've got tension, and that's it. And then for long range forces, we have the force of gravity, and we'll call that FG1, force of gravity on mass 1, just to distinguish it from mass 2. And since we're accelerating downward here, I'm going to go ahead and do my trick of decreeing that down is positive. But if you want to do up as positive, that's fine. Just make sure you substitute in a negative A when you do your Newton's second law expression. All right. So let's go ahead and draw a free body diagram for mass 1 here and see where we get with that. So we're going to have the force of gravity down, and we're going to have tension up. And yeah, that's it. The problem is we don't know what the force of tension is. So we're going to have to analyze mass 2 to come up with an expression for the force due to tension so that we can substitute in. But we can take it as far as we can. So let's go ahead and do that. This is going to give us, if we say F net equals MA, so this will be FG1, well, I'll write it that way, FG1 plus T equals MA. We'll take the Y component of it. Gravity is pointing down by decreed down was positive, so it'll just be FG1. tension is up, and I decreed that down is positive, so that means up is negative minus t. Since I decreed down is positive and the acceleration points down, that'll just be a, which is why I did it that way. And I should make sure that all those m's are m1s since it's mass number 1. All right. Well, poo. We wanted to solve for the acceleration, but we ended up with an unknown tension that we're going to have to now deal with. We don't need to solve for it numerically, but we're going to have to deal with it. So let's go look at this and hope that we don't introduce anything else when we solve for the tension. So, okay, here the circle cuts through the string, yay, and it cuts through the surface here, boo. All right, so there's going to be a normal force acting on object 2. And because we said the force of the coefficient of kinetic friction was non-zero, that means there will also be a force of kinetic friction. And we ask and that's it for that surface. There are no more surfaces. So ask for the long range forces. All we got is gravity. All right, same deal. Let's draw a free body diagram for this. So we will have a force of gravity down, Fg2. We will have a normal force up. We will have a force of kinetic friction to the left since it's moving to the right. And we'll have a force due to tension in the string pulling to the right. And these two tensions here are a pair that act as if, I want a more distinct color there, are a pair of forces that act as if they are an action-reaction pair, using that annoying phrase. So they're not opposite, but they are equal, and the whole issue is going over that pulley, that whole bit about the combined second and third law pairs I mentioned in an earlier video. All right, so with that, let's go ahead and analyze this. So again, here we're going to write, F net equals M2A here. All right, so what are all of our forces? They are normal force plus gravity plus tension plus force of kinetic friction equals M2A. And we'll take this into components. So in the land of well, let's actually do the land of Y first. When you do problems with friction, it's usually beneficial to do the land of Y first, or whatever land you need to be in to figure out the normal force. You know you're going to need the normal force to stick into kinetic friction, so that's usually the safer thing to do. So with that, let's go ahead and go into the land of Y. The normal force acts entirely up. Gravity acts entirely down. And that will equal M2 times the Y component of the acceleration, but that's 0. So we get that the normal force is Fg2, so it's M2G. All right, now let's go over to the land of X. We have tension acting to the right, kinetic friction acting to the left, and that's all she wrote. It's accelerating to the right, so we can just say M2 times plus A. And this is why I did this, to get this expression for the normal force, because when we put in our expression for the coefficient for the force of kinetic friction, this will be the coefficient of kinetic friction times the normal force. And so we want to be able to put in the normal force. Otherwise, you have to pause and solve for it, which isn't the end of the world. All right. So we've got two equations and two unknowns. Our unknowns are the acceleration, which we want to know, and the tension, which we don't care about. So we can do, You can do it however you like. In a previous video, I did it where I added the two equations to make the tension go away. So here, just to change it up a bit, I will go ahead and solve the, let's solve the FG1 equation for the tension and stick that into the one for mass 2. So taking this one here, this is going to give me the tension is equal to Fg1 minus M1A. So it's M1G minus M1A. Okie doke. So let's pull on M1. There we go. All right, so now that we've got that expression for tension, let's put it in over there. So this will be M1G minus A. I probably shouldn't have grouped it, should I? Because I'm solving for A. Sorry about that. Let's just leave it there. So sticking in, we will have M1G minus M1A. So we'll have M1G minus M1A minus mu K M2G equals M2A. Now we're solving for A. So the first step is just to get everything with A on one side of the equal sign and everything that doesn't have A onto the other side of the equal sign. So let's go ahead and do that. So we'll have M2A, and if I add M1A to both sides, it'll give me M1A plus M2A. And then what do I have left? I have M1G minus mu K M2G. All right, let's group out common things. There's an A in both of these, and ultimately we want to solve for A, so it'll be a lot easier if we group it. So M1 plus M2A. You might wonder why I didn't put the A out in front. Mathematically, I could. It just turns out that there's sort of a standard order that physicists write things in. They tend to write numbers first, so just digits, 1, 2, 3, 4, 5, whatever. Then they write named numbers, so that's things like pi. Then they write constants, so that's things like, you usually tend to write things like constants. Then after that, you have parameters and variables. So thing like a coefficient kinetic friction is a parameter. Variables, the thing you're solving for, is the thing that you would presumably measure in an experiment. A parameter is the thing you'd adjust between experiments. Anyway, all that to say, physicists usually put the A to the back. And same thing here, G would be toward the back compared to these. So you tend to write as M1 minus mu K M2G. So we get that the acceleration is M1 minus mu K M2. We don't need that parenthesis, over M1 plus M2G. Now, we can go ahead and start sticking in the numbers and solving. So sure, let's go ahead and do that. But look at this for a second. Just even before we go on, looking at it as a collection of letters, you might already start to think that you're on the right track. You ask yourself, where have you seen a solution that kind of looks like that before? Okay, I'm hoping that you said it kind of looks like Atwood's machine, and it would be if it weren't for that mu k. And if you think about it, that kind of makes some sense. The difference between this and Atwood's machine is that in Atwood's machine, we just let it roll over. And so the thing that was opposing tension on the other side was gravity, and now it's kinetic friction. So you wouldn't be surprised that the expressions look similar, except that something to account for the friction needs to show up. Again, okay if you're not catching that right off, but this is, again, part of why working in letters as long as possible helps, because you can start to recognize old friends as you go along the way. All right, let's stick in our numbers. So 1 kilogram. Oops. Come on. 1 kilogram minus 0.2 times 2 kilograms over 1 kilogram plus 2 kilograms times 9.8 newtons per kilogram. And since we're solving for an acceleration, we'll just observe that a newton per kilogram is dimensionally meters per second squared. Grind this through on your calculator. You will get 1.96 meters per second squared. Again, when looking at numerical plausibility here, this seems reasonable. You know that it's got to be bigger than 0 because it ain't going to fly up here, just from common sense. And you know if you cut the string, it would fall at 9.8 meters per second squared. But since you have force pulling up, it needs to be less. So we got a number that was between 0 and 9.8 meters per second squared. So yeah, we can go ahead and call that one reasonable. All right. One other thing that I'll go ahead and put into this bit of applications here is just a dirty trick that is helpful for certain problems. I like to call this cleverly choosing your free bodies. And what do I mean by that? Well, maybe one of the best examples I can think of is, let's say you've got like 3 crates. I'm not actually going to work through solving this too much, but I just want to give you some sense that this is maybe easier to solve. So let's say I've got 3 crates like so. And it's attached to a rope. So we'll draw a rope. And so there's tension T in the rope. And we can assume that we've got, and these are hooked together with, ideal physics ropes here as well. And so let's say you're being asked to, so this is given. And you're being asked to find the tension in strings 1 and 2 and the acceleration of all of these masses, because you know they're all going to be the same because they're moving in lockstep. So let me show you, so you can go ahead. Actually, let me copy this and make a copy of it here. Copy, paste, move that one down, say there somewhere. Okay. So I want to be abundantly clear. There's absolutely nothing wrong with doing these the way we've been doing them, which is where you choose your free body sort of the obvious way, like so. And we can go ahead and, let's make sure there's a surface on here too. And we'll just make friction 0 so we don't have to worry about friction. Let me go stick a surface down here as well. All right. So you can certainly do this. And if we do check our force identification here, this will cut through rope 1, so we'll have a T1. Then we'll have a normal force no friction because we said it's frictionless, and a force of gravity. Here, though, this would cut through both T1 and T2. And a normal force, we'll call this N1, N2, Fg2. Then here, we would cut through T2 in our given T without a subscript. And then we'll have normal force 3, again, no gravity, because no friction because we turned that off, and Fg3 for gravity. All right. And you could certainly go ahead and draw the free body diagrams for each of these. So we'll have normal 1, Fg1, they're going to cancel by the second law, it'll turn out, and just T1 to the right. So in the land of X, when we do our Newton's second law stuff, this one will just be T1 equals M1A. All right, that's not too bad. Let's do our second free body. So here we'll have T1 acting to the left, and that's the third law pair. We'll have T2 acting to the right, like so. And N2 and Fg2, again, those are vertical. So when we go to the land of X, we're going to get T2 to the right minus T1 equals M2A. Then when we draw our third free body, like so, we'll have T2 to the left, T3 to the right, N3, Fg3, and in the land of X, when we balance our forces, sorry, not T3, this is just T, our given T. We'll have T minus T2 equals M3A. So this is known. And so you can go ahead and solve it. You can solve this for T1, stick it into here, solve that for T2, stick it in there, and then you can eventually solve the whole thing for A. It's doable, but maybe a little faster is if we get clever with the physics to make the math suck less badly. Because if you think about it, when you look at, say, a box, you might have been asking yourself, well, why don't we have to worry about every single atom individually? Why can we put a circle around an entire box and not have to worry about how the individual atoms interact? And we'll touch on that a bit at some point, but a full-blown proof is beyond the scope of this course. But suffice it to say that you can show that interactions that are merely there to hold the object together don't count. And so that means that you can be maybe a little more expansive thinking about what are your, what does your object look like? And maybe you can make things that you don't like too much not count. What do I mean by that? Well, let's try this collection of free bodies. So here the idea is that I need to solve for A, but I don't like this T1 and this T2 business. I mean, I'm going to have to get them eventually, but let's say I just want to get the acceleration. If I just want to get the acceleration, I could make the whole collection of these one of my free bodies. By doing that, I take the tensions in the ropes, and those just become merely details about how the whole composite object is holding itself together, and I don't need to get myself concerned about them. So, and then to complete the sleigh ride here, because I do want to solve for, so this will give me the acceleration right away. And then once I have the acceleration, I can then go back and make that a free body. That'll give me T2. And I can also go back and make just that a free body, and that'll give me my T1. So let's work that out. So we'll start with the outermost of these. So here, this object is this dot here is representing the combined M1 plus M2. Oops. Plus M3 object. So all you got is our given T to the right, and that's it. I mean, of course, we've got normal and gravity up and down, but that ain't happening in the right. So that means when we write down the x component of Newton's second law, we can just say T equals the mass of the thing, which is M1 plus M2 plus M3A, and just immediately get that A is our given T over M1 plus M2 plus M3 without having had to eliminate the T1 and the T2 along the way. Then getting T1 and T2, now that we've got the A, let's go take a look at finding T1. To find T1, let's just look at this free body right here. Just M1. So there, now the dot just represents this one crate, M1. The force pulling it to the right is T1, normal and gravity again, which we're not too concerned about here. But we can just immediately say, taking the x component of Newton's second law, T1 equals M1A, and we found A, the value of A from the previous part, so you can plug it in. And you can do the same thing for finding T2. We go ahead and use this system, the combined M1 plus M2 system. Whoops, let me make that a little lower. Again, normal, gravity. Again, we're not stressed about those since they're in y and we care about x. So taking Newton's second law in the x direction here again, the only force I have acting is T2. It's equal to M2A. And I can take, M1 plus M2A, because that's the mass of the composite thing. But I can take that same solution from A that I got before, stick it in there. So, I mean, to be clear, if you don't see the clever way right away, absolutely nothing wrong with doing this. It's just the algebra is going to be a bit of a chore, but you'll get exactly the same answer. But here, if you can sit and think for a second, sometimes, especially in a situation like this where you're recognizing everything's accelerating the same or something like that, sometimes you can get away with doing this composite free body trick. And by us cleverly using our physics, we can make the math less ugly. So, all right, catch you on the flip side.